to have this in a microscope, come on, we don't need those cuvettes. We have the cell, the proteins are there, of course you have to put the labeled proteins inside the cell. That's the difficult part. But once you get that, this is your cuvette now. And you have an observation volume that you can put anywhere in the cell. In any place you want. So you can observe and take data from any place of the cell. This kind of data. And, well, with time, people kept working on techniques for dynamics using fluctuations, and then they came up with scanning FCS that also was developed in the LFD, image correlation spectroscopy, spatial temporal correlation spectroscopy, image correlation spectroscopy, and raster image correlation spectroscopy. That is, since you have in a confocal microscope what we do, we have that point, that observation volume in the cell, we scan it, and we get an image. That means we have data from each point in that plane of the cell. So we can recover dynamic information from that images. Actually, we have different time frames for a set from a sequence of images that we can use to calculate correlations. We have the time interval between pixels, that will be very short, time interval between lines, that will be in the order of milliseconds, and the time difference between frames. So we can try to relate, for example, fluctuations of the same pixel in different frames, so we'll have a time interval of seconds. Relate correlation between neighbor pixels, we have a time correlation of microseconds, and it goes on. So we can have dynamic information for the whole image, and if we are able to do the experiment well, for the whole cell. And also, what I want to show you is how we can use these characteristics of the small volume of excitation to do real-time 3D tracking of fluorescent particles inside these living cells. And this is, I'll show you some data Andrea and I obtained when we were, Andrea is a professor that's sitting there that happens to be my wife too, and we have been working in, as a foreign concert in the LFD doing, trying to track various particles that, that were infecting a cell. And I'll try to show you how it works and how we use that to get information about the conformational change of the particle during this process. Now, remember that small volume, that is our observation volume, and that can be scanned, right? So imagine now that, well, that volume, the characteristic of that volume is that at the center of the volume, fluorescence intensity is the highest. At the periphery of the volume, fluorescence intensity is lower. So imagine we can make an orbit with our volume that is half the size, meaning the center of the excitation volume is here at this line, this circle, and this is the periphery of the volume. Now imagine that our fluorescent particle is right at the center of this orbit. What we will see, our fluorescent signal will be always the same because it's stopped there. We are making this orbit and taking data, so the fluorescence data will be always the same. It's here, stopped. But if it moves, what we will see is a modulation, because once the particle gets closer to the center of the excitation volume, fluorescence intensity increases. Since this is an orbit, what we see is a modulation of the signal related to the point of the orbit we are. Monotonical modulation. So from this modulation, we know where the particle is going. We know what's the direction of the movement. If we have the system always measuring this modulation, we know what's the direction. It's directly related to the position of the particle. So imagine we have a particle there, we measure this modulation, so we recenter the orbit at the point we measure the highest signal, like this. Then we start all over again and recenter the orbit each time we calculate a new point. we can actually track the particle and see exactly where it's going. Now, imagine we do that in two different planes. So we have our objective moving up and down. The mirrors are doing the orbit, are making the orbit. The objective by a piezo system is going up and down. So we do one orbit at one plane, and again, half that distance of our, let's call the PSF, or point spread function, is what describes this excitation value. With half the PSF, so we again have the maximum of intensity at the center and the minimum at the periphery. So if we have the particle at the center, we will measure same signal up and down. If the particle moves, it increases in one of the planes, and we also know if the particle is going up or down. So with this system, we can track in real time a fluorescent particle with our microscope. And this is actually quite nice because the major technique that is used for tracking fluorescent particles is using a very fast CCD camera and take a sequence of images of the particle moving. Then you determine the centroid, or exactly the center of the fluorescent spot, and you follow that spot, so you determine the trajectory. But this is limited to a plane, to 2D. You cannot do 3D. And as we know, cells are intrinsic 3D systems. They are not plane. And particles move all around. They are not moving only at one plane. So once the particles go out of the plane, you lose it, you have to start all over again. With this system, we can follow in 3D, in real time. Of course, what will be the resolution? Resolution will be a fraction of the PSF, and it's not as good as when you calculate the centroid of the fluorescence spot, but it's faster in vivo. Well, it can be, it's not faster, sorry, it's feasible that you do it in 3D, so there is a big advantage. Time resolution here will be determined by how fast you can do the orbit and how fast you can move it up and down. The system we were using, we could do these two orbits in 60 milliseconds. So every 60 milliseconds we were determining a new point and going after the particle. Well, this is just an example. If the particle moves in X, Y, and in Z, what we will see is that modulation we saw before, or kind of a quadratic function for a Z movement of the particle. So from this information, we can calculate the coordinate, the 3D coordinate of the particle using repositioning on the fly the center of the orbit and the center of these two planes. We can keep track of the particle. Well, how does it relate to virus infection sites? Well, we wanted to follow the early events of the infection cycle, and it's very difficult because it's not like at the end when the virus infects the cell, it produces a lot of material and there are lots of particles coming out. There is very little material during this period of the infection cycle, and it's very difficult to observe that. How can we do that? Well, by immunofluorescence, using immunofluorescence, then you have to fix the cells. We don't want that. We want to observe the process in real time. We could do fluorescence imaging different times, or time-lapse experiments. It's static because each image is a different point of the process. There is a lack of information. There is no 3D. Time interval between frames is too big. And you need, in order to observe anything, you need large amounts of virus. What doesn't happen naturally. We can track using cameras, but again, it's restricted to one plane and needs to illuminate the whole cell. What many times causes the death of the cell. You see the cell dying, and you cannot observe the process anymore. It dies before the process is complete, before the infection process is complete, before the virus entrance is complete. How our system solves this problem? We can track a single particle. Why? Because we have the laser pointing at a single particle all the time. Second, we don't need large amounts of virus because we need only one particle, actually. Of course, it's very hard to find one particle when you try to do the experiment, but once you find it, you are able to follow. We can follow the infection process in real time, in 3D, and inside live cells without needing to fix that. So we can gain insight on the virus-cell interaction mechanism during the early steps of the infection cycle. And the virus we have chosen to follow was rhinovirus. Rhinovirus is the common cold virus. So every one of you knows it, know it. You have been in contact with that. Probably you are in contact right now. It's a very small particle. It's 30 nanometers particle. Viruses are being very trying to reduce it to the simplest system, because of course it's more complex than that, but it's more or less like a protein coat with some genetic material inside. So what we did to follow it was label these proteins with fluorescent, just fluorescent, and make a fluorescent particle that is 30 nanometers, that has 30 nanometers of radius, actually diameter, and infect the cells. So we incubate the cell with the virus particles. We find the particle. This is a two-photon excitation image. We find the particle. We point the laser at the particle and start tracking it. And this is the projection of a trajectory on the 2D image of the cell. Wow, nothing. There is not much information there. But, sorry. This is the 3D trajectory. Actually, it moves a lot in Z. A lot. And this is not observed at all if you do the camera tracking. You cannot observe this kind of stuff. You cannot observe this movement. Most of the movement is on the Z. These are all the coordinates, all the values of X, Y, and Z we can recover from the experiment, and this gray line is fluorescence intensity. Since we have the laser pointing at the particle during the whole experiment, we have the fluorescence emission trace of the particle. So we can use that in order to get information about conformational change. At the same time, we track the particle. Of course, well, if you pay attention, you'll be surprised that this is 1,600 seconds, and fluorescence intensity is constant. There is no bleaching. We will try to explain that, and actually it's very interesting. These are the 3D trajectories we recovered for the particle when we incubate with at 4 degrees. What happens? The particle attaches to the cell, but it doesn't go in, because in principle we think this particle goes into the cell by endocytosis. So we tried to reduce the temperature, to stop endocytosis process, and then we started tracking. You can see the movement is restricted to a very small volume. This is in nanometers, this is scales. If you can see the values, I don't know if people over there can see, but this is more or less 200, 300 nanometers. The particle is stuck at the membrane. This is what we are observing here. Then we increase the temperature to 37. Particle goes in, and then it moves, well, 1.6 micron inside the cell. Most of the movement is in Z, restricted to this axis, what gives us the strong suggestion that the process is directional. but actually it's too slow. We can calculate apparent diffusion coefficients for this particle. Of course, it's not freely diffusing, but we can measure diffusion. Well, since this process seems to be active, we can calculate a velocity for this. And this gives us the information that it's not very fast. It's not as fast as we would expect for an endocytosis process with process motors carrying the vesicles inside the cell. So this is something else. And after some time, actually after more or less 30 minutes, we see that the particle stops again. But this is in a plane in the middle of the cell, close to the nuclear region of the cell. And again it stops and it starts moving from apparently one plane to another, hopping around. Okay? So it seems that it's experimenting different environments close to the nucleus, and this could be related to RNA release inside the cell. We have to investigate that. But, well, these characteristics suggest that particles interact with different transport systems in the cell. We try to investigate it. We use it, microtubules and microfilaments in inhibitors. We see here the control experiments, totally either quintubulin or the, sorry. This is a control for the microtubules and inhibition and microfilaments inhibition. And what we see is that when we incubate the cell with the inhibitor and with the virus, well, when we inhibit microtubules, it still moves in zinc. But when we inhibit microfilaments formation, then it's stuck. So we see that this. Okay.
Can I just ask, what is special about the Z direction? Is that just, it's like coming into the cell through the Z direction?
Yeah, but as you can see, it goes, sorry. Yeah, it's in Z direction. But as you can see, this is directional. This moves in a very special way. It's not just going and diffusing inside the cell. It's moving somewhere. So there is a transport process that's not endocytosis, that is acting for this particle to go to a specific place in the cell. And from this experiment, we know that it's related to microfilaments and not microtubules. But we still don't know exactly what is being used for taking this cargo to this region that's close to the nucleus.
Yeah, the Z direction is not fixed. It's just because you have to separate one of the X from the plane completely.
Oh.
I didn't know the cell was like flat.
Yeah, that's a moment.
Well, yeah, the cell is a volume it has in the, well, at the peak it can be 12 micrometers. This is animal cell. And also, there is more information on it than the coordinates of the motion. Actually, intensity data, the gray line, is collected during the whole experiment, and first of all, it showed no photobleaching. It's a lot of time. And showing no photobleaching is very special in this case. Also, well, there is an oscillatory pattern. As you can, if you can see that, it's not constant. There is an oscillation, a fluctuation of the signal during the process. And, well, this can be related to conformational changes of the particle. We try to observe that. It's known, well, let's try first to explain why this happens. We label the surface of the particle with many, many probe molecules. They are very close together. And this is fluorescein. Fluorescein has excitation and emission spectra that are very close to each other. So one molecule of fluorescein transfers energy to another molecule that is very close in space. Close and well-oriented in space. So that is energy transfer. And so we call it FRAT, it's homofrat. And if there is energy transfer, lifetime would be very short. What's the lifetime? It's the time the electron stays on the excited state before it comes back to the ground state. So this is when the photobleaching reactions happen. If this time is very, very short, there is no time for the reactions to go on, so there is no photobleaching. So very short lifetime would protect from photobleaching. We measure the lifetime inside the live cell doing fluorescence lifetime imaging microscopy. And what we could see, well, this is the phaser approach. I'll not talk a lot about this, but this is an approach that was developed in the LFD when we were there. And instead of doing many fittings to calculate lifetime from images that were taken different frequencies of modulation of the light source and things like that, what is very difficult, the lifetime data is converted to a graphic. And this shows all the pixels in the image, and the place where they are here are related to the lifetime, to modulation and phase lifetime. So when we select it here, we have the values of the lifetime here for phase and modulation. These different values mean we have different lifetimes. If it was only one, we would have a very close values here. But what we can see is an average of all these pixels that we are selecting here. Actually, when we select this area, what we are selecting is the cytoplasm of the cell. The particle is not selected. So I don't know if you can see, probably not, but there is a very thin tail here that are pixels that have much shorter lifetimes in this image that we are not selecting here. When we select that region of our graph, now we are selecting the particle. And then we have the lifetime, much, much shorter than we would expect for fluorescing. That's about 4 nanoseconds. We have something about 0.2 nanoseconds. That gives a good indication that, yes, we have energy transfer and we have a very short lifetime, and probably this is protecting our particle from photobleaching. Now, it's...
So what is exciting in the cytoplasm?
What is this? Well, this is autofluorescence. It can be flavins, can be NADH proteins that are bound to flavins, NADH, FAPERJ, and things like that. And autofluorescence of the proteins in the cytoplasm. It's described for this virus that there is some dynamic of the capsid that was called the breathing of the particle, where it was shown indirectly by mass spectrometry data, where they incubated the particles with proteases. And what they could see is that proteins that were inside the capsid were being digested before the proteins that were outside the capsid, meaning that there was access to it. And so they proposed that there was some dynamic of from the structure they determined for the particle, there wouldn't have space for the proteins to go inside. From this data, they proposed that there was some breathing of the particle. Well, I imagine that our particle is labeled and there is energy transfer. Energy transfer is dependent on distance. So if the particle has this conformational dynamic, distance will increase, and what we will see is that the intensity will change with time. Remember that we have an oscillatory pattern of our fluorescence intensity. That it is. So we have fluorescence fluctuations. And we know how to study this. We do FCS. So we take this fluorescence trace and calculate the autocorrelation function for this. And it shows nothing. This autocorrelation is actually tricky to interpret. But when we do the distribution of the fluctuations, we actually see two different populations here. One more intense, one less intense. And they could be related to different states of the particle, right? So we tried to separate this. we went back to the trace and separate two parts. This initial part and this final part of the trace. And we calculated the autocorrelation function. They look very different, and we separated the calculations. So during the process, the particle is changing. And it's changing in a way that this particle has higher fluorescence intensity, this particle has lower fluorescence intensity. That means this, as I will show, I think it's here. If intensity is higher, that means FRET is less efficient. If it's less efficient, we have a larger particle. So it fluctuates. Actually, we are watching conformational fluctuations of the particle during the inflection process. From the autocorrelation functions, actually, we cannot get much information, but we can see that the frequency, well, you see the profile of the autocorrelation here and here is different. So we know that the tau, that value, that time constant of our system is different for this particle and this particle. So this is related with the frequency of the conformational dynamics. Okay, I'll finish. We measured again lifetime. So if it's larger, FRET is less efficient, lifetime should be higher. It is 1.6. It's not the 4 nanoseconds we would expect. That means it's still a particle. It didn't disassemble. Well, so what's probably happening? We have lower frequency and higher amplitude at the beginning of the process, as shown by the autocorrelation and the distribution. And then we have cell entry, and then we have higher frequency and smaller amplitude. So the particle expands. During the process, the size of the particle increases. This could be related to the interaction with the receptor, or this could be related to RNA release. Actually, we are trying to do the experiments now with double labeling, labeling the genomic material, labeling the protein material, and we'll try to see them splitting during the entry. And our system can do this. We can follow two different particles. It goes to an orbit here, calculate, then goes to the other, calculate position, and it keeps switching and following both particles, if they are going on, of course. Okay? So, well, this is something that was here for something else. Thank you very much. Thanks to Enrico, that was the boss there. Valeria Lev, that helped us a lot with the tracking system. Susanna also, all the laboratory for forensic dynamics, that includes you, Candice. And our collaborators with the virus, Professor Jason Silva, Ivanildo and Carlos, that are the students that work with me. And they are here because of some data that I didn't show about the cell, but they are helping a lot with the system. I couldn't be here during the week because we are just setting up the system in our lab in order to do this here in Brazil. So thank you very much.
We have time for a few questions.
Yeah, two questions. The first is, you say the virus is expanding. Can you quantitate or get a guesstimate for how much it's actually expanding?
Well, actually, yes. If we can, we will try to do that now that we have the equipment here. But if we can measure the FRET efficiency for both states, we can calculate the distance between the probes, and from that we can try to find out what's the scale of this expansion.
Okay, and the second question, and this might be a very stupid question, but is there a chance of you losing your particle? You say it's in the sphere, and your particle moves in each snapshot. Can you lose it?
There is a chance of losing it, but what happens is the system is configured to do something. It increases the radius of the orbit until it finds again the fluorescent spot. Then it repositions the orbit at that point and starts falling again. It happened.
And how big are these orbits?
How big?
Yeah.
The radius of the orbit is half the PSF of the microscope.
But I can't remember, when you did these measurements, did you do it when you had to take the dose? You were doing simultaneous?
I can't be inside.
I can't remember because now the system has upgraded where you do simultaneous.
Sorry.
Now the system, I can't remember because I was trying to finish up too. But anyway, I can't remember when you did these measurements, did you do these simultaneous lifetime, like film and?
It wasn't there yet.
Yeah, but now it's there, so that's why.
Yeah. Well, we are beginning to talk with Susanna, that's in contact with Oliveira, and we will try to do that. Yes.
Two quick questions. First, the Z dependence that she asked also. I suppose it's probably because when you're tracking, you start by a spot that is at the top of your cell.
Yeah, exactly.
Right?
Yeah.
So
well,
second,
actually, we find the particle. At the first moment, we didn't know where it was. Then we found the particle, started tracking it. Then we wanted to know, well, where are we beginning? So we were seeing this motion in Z, but then we labeled the membrane with Lorden, and then we took a Z stack of the cell, so we could see the membrane, and we could localize the particle with the other structure of the cell. So we know exactly where we were starting.
So I was going to ask, can you use this technique to actually look at buckling transitions in viruses?
To look at?
To look at the buckling transition in icosahedral viruses. So when you have an icosahedral virus, you change salinity, pH, those sort of things, and they'll do this swelling, and you can see whether, based on their size, they'll actually undergo a transition from a roughly spherical to a really sharp icosahedral structure, and that's called a buckling transition. I was wondering if
you
you've done.
Can relate the present signal with this change, yes.
So,
but you have to see the difference in intensity. Otherwise, there is no way to follow it.
Yeah, I was just wondering if anybody's done any experiments like that.
I'm sorry, I have a question because from the data you already have, did you look at the second moment to check shape? Because when you
because
then that will answer.
Actually, at that time, the analysis of the second moment were not at that software. But I was talking to Enrico about that, and yes, it's possible. If you look at the second moment, you analyze the orbit, and you can see what's the shape and what is the translation of the shape during the tracking.
Yeah, just a comment. I mean, yeah, it's principle, yeah, but still resolution, space resolution.
Yeah.
But the principle, yeah, is maybe combine several.
Resolution for the steps here are 30 nanometers. I don't know what will be the resolution for the shape. Maybe
exactly.
We can talk about Nico and all about that.
Yeah, just one more comment. I mean, there are for some of these viruses that they're trying to develop drugs and so forth, and especially with coronavirus people, there are some people that believe that the particle only gets into the membrane and then inject the nucleic acid. I think if you have an image, that's everything. I mean, so.
Well, actually, it's very interesting because yes, there was this description. People thought that the virus would attach to the membrane and inject RNA because they found empty particles on the surface of the cell. But actually, well, there was still this discussion. It could be particles that would go inside, inject RNA, then be recycled to the surface. And yes, it could be, since we see that lifetime is not what we expect for just fluorescent protein complex, it's still short, that means there is still a particle. And if RNA injection already happened, this would be the description of the process. The particle goes inside, injects RNA, and is recycled to the surface of the cell.
Okay, well, if there's no further questions, so we're going to have some dynamics data, so let's thank again.